Okay there, Corey. We're going to finish chapter 1, Motion, Forces, and Energy. We will be in section 3, which is page 19, right, Landon? So we're going to look at mass and inertia. Now, inertia, both these words are very specific science words, Anna, that need some good understanding. All right. The world you live in is filled with objects in motion. How can you describe these objects? Objects have many properties such as color, size, and composition. One important property of an object is its mass. The mass of an object is the amount of matter in the object. In SI units, which is the international standard, the unit for mass is the kilogram. Okay? So you see a yellow word here. Do you think you know what's the first thing we might write down? But we need to make sure our outline is right. All right. The weight of an object is related to the object's mass. Objects with more mass weigh more than objects with less mass. A bowling ball has more mass than a pillow, so it weighs more than a pillow. However, the size of an object is not the same as the mass of the object. For example, a pillow is larger than a bowling ball, but the bowling ball has more mass. Objects with different masses are different in an important way. Think about what happens when you try to stop someone who is rushing toward you. A small child is easy to stop. A large adult is hard to stop. The more mass an object has, the harder it is to start it moving, slow it down, speed it up, or turn it. This tendency of an object to resist a change in motion is called inertia. Objects with more mass have more inertia, as shown in Figure 12. The more mass an object has, the harder it is to change its motion. So our two yellow words here is mass, which is the amount of matter in an object. It is not the weight of the object. You must realize that. And then inertia is how hard it is to change an object's motion. Now, remember that the difficult thing with inertia is that if you are at rest, you can change your motion by starting to move. All right, so we are going to look at our notes. Okay, Josh, here we go. So we have Roman numeral 3 because this is our third section in the chapter. Capital A is our blue heading, mass and inertia. We do not have any little red headings, so there's no 1. Okay, remember I just said mass is the amount of matter in an object. All right, B, the more mass it has, the more weight. So they're not the same thing. Okay, the more mass it has, the harder it is to stop. The inertia is the tendency of an object to resist change, and we will talk about this a lot. And then the more mass it has, the more inertia it has, the harder it is to change its path. Okay? All right, so momentum. You know that the faster a bicycle moves, the harder it is to stop. Just as increasing the mass of an object makes it harder to stop, so does increasing the speed or velocity of the object. The momentum of an object is a measure of how hard it is to stop the object, and it depends on the object's mass and velocity. Momentum is usually symbolized by a P. Why? I don't know. Can't be M, can it? Because what is M? M is mass. All right, so momentum is the mass times the velocity. Well, mass is kilograms, velocity is meters per second, so momentum is kilograms, meters per second. Okay? Mass is measured in kilograms and velocity has units of meters per second, blah, blah, blah. I just said that. Okay, so because velocity includes a direction, momentum has a direction that is the same direction of the velocity. Okay, so your momentum is your mass times how fast you're moving. All right, let's take a look Let's see, Kyle, what we have next. All right, so momentum. Momentum is the measure of how hard it is to stop the object. It depends on the object's mass and velocity. Momentum is shown as P. P equals the mass times velocity. And units are kilogram meters per second. All right. Now we've missed some pictures, haven't we? We had a picture here, didn't we? Let's see. All right, go back to page 19. All right, so the more mass an object has, the greater its inertia is. A table tennis ball responds to a gentle hit that would move a tennis ball only slightly. Okay, so if you hit a tennis ball with the same force that you hit the ping pong ball, the tennis ball wouldn't go as far because it has greater mass. All right. So we did that. And conservation of momentum. Okay, again, this is big time science stuff. You see your yellow words here, okay? Let's look at the example. If you've ever played billiards, that's pool, table pool, right? You know that when you hit the cue ball hits another ball, the motions of both balls change. The cue ball slows down and may change direction, so its momentum decreases. Meanwhile, the other ball starts moving, so its momentum increases. It seems as if momentum is transferred from the cue ball to the other ball. Okay, Christopher, in fact, during the collision, the momentum lost by the cue ball was gained by the other ball. This means the total momentum of the two balls was the same before and after the collision. This is true for any collision as long as no outside forces, such as friction, act on the objects and change their speeds. According to the law of conservation of momentum, the total momentum of objects that collide is the same before and after the collision. This is true for the collision of billiards balls as well for collisions of atoms, cars, football players, or any other matter. Okay, so the momentum of the objects, the velocity will change, but someone else, it's transferred to something else. So here's the pool. When the cue ball hits the other ones, it slows down because it transfers some of its momentum to the other billiard balls. So think about the speed of this, and this is one ball hitting 13 other, 13 other balls. Okay, so this mass equals 13 of these. Well, 13 times. It's hitting something 13 times more mass. That's why when you rack your the pool balls, they'll have to be touching each other because then they act as a solid unit. If you have any space in between, it's like if this guy doesn't get pushed in all the way, he won't go as far because there's a little bit of space here. When these are hit, they're going to travel a little bit before they hit the yellow ball. So I like this predict. What would happen to the speed of the cue ball if all of its momentum were transferred to the other billiard balls? Okay, if it had no more momentum when it hit these, what would happen to the cue ball? I want you to tell me that tomorrow. Okay, Hunter, here we go. Conservation of momentum. This big time stuff. Okay, this A needs to be in a little bit, doesn't it? The law of conservation of momentum. The total momentum of objects that collide is the same before and after the collision. Okay, we will work with this for a good little bit, especially with our cars and the ramps. All right, using momentum conservation. Outside forces such as gravity and friction are almost always acting on objects that are colliding. However, sometimes the effects of these forces are small enough they can be ignored. Then the law of conservation of momentum enables you to predict how the motions of objects will change after a collision. There are many ways that collisions can occur. Two examples are shown in figure 14. Sometimes the objects that collide will bounce off each other, like the bowling ball and bowling pins. In other collisions, objects stick together after they collide, like two football players. In both these types of collisions, the law of conservation of momentum enables the speeds of the objects after the collision to be calculated. So we have a collision here where things collide and bounce off each other. Okay, the bowling ball does not dent the pin and stick to the pin. Okay, it causes the pins to move, it transfers some of its momentum. What would happen if the bowling ball had less mass than the bowling pins? Would the pins move? I don't know. How about this, when we stick together? Okay, momentum is still conserved, but now we have one moving object instead of two. Now, let's look, well, let's go back a minute. Okay, because the rest of the section describes the sticking together, the two types of collisions. But we're not going to worry about all this. Okay, this is a little too much information. And when we do these problems, we'll work it out then. But just understand that you can have collisions where things stick together. And that means that the total momentum is the two different things. Like if you throw a backpack at someone who's on roller skates. Okay, the backpack has momentum, you on roller skates have momentum, and then the total momentum is both of these added together. Then you have the case of colliding and bouncing off. So this bumper car has momentum, this bumper car has momentum. When they collide, they bounce off each other with different, they each have different momentum, but the total momentum is the same. Confusing, confusing, confusing. Oh, look at that, Parker and Christopher. Explain how momentum is transferred when a golfer hits a ball with a golf club. Ooh, that's interesting. All right. All right, Montgomery. Let's see. Last one. Using momentum conservation. Okay, we can stick together where objects collide to make one moving object. Or two, we can collide and bounce off, Ethan, where two objects collide and result in two objects. Okay, so this is plus, plus equals one thing. This is plus, plus equals plus, plus. Ha. All right, so I want you to tell me, is this a sticking together or is this a bouncing off? Okay, in this type of collision. I wouldn't want to be me. No way. Or my Andrew, who's driving now. All right, guys. Bye. Have a good night.